I'm Michael Starzinger. I work as a software engineer at Google. I work on the V8 team. V8 is for those who don't know, is the JavaScript engine that's powering Chrome and Node.js. I've been working for Google for 7 years now. And fun fact, before that, I actually lived in Vienna for, I think, 8 years. So being able to talk here and then being invited here actually brings back fond memories. So that's great. Before V8, I worked on an open source Java VM, so anything to do with compilers or virtual machines is super interesting for me, so I love it. All right, but enough about me. Let's talk about V8 actually. The things I want to talk about today are our new compilation. Yes, does it work? Yeah. Our new compilation pipeline. Our compilation pipeline is basically a tale of 2 compilation tiers. And compilation tiers are basically levels of optimization that we can apply to your JavaScript application. Yeah. Also, the optimizing compiler that we use uses speculative optimization, so I want to talk about that a little bit. And how it's based on feedback, because that might be interesting for application developers, how we actually optimize the JavaScript code. And one particular optimization I want to go through is inlining, because it's the mother of all optimizations, so to say. It enables a lot of other optimizations. And then in the second half, we'll look at 2 examples. First one is the inlining of higher order built-ins that we do. And the second one is JavaScript generators. So that will keep us busy for a while. Yeah, kann ich probieren. All right, let's start with the compilation pipeline. As I said, it's a tale of 2 compilation tiers. The 2 tiers are made up of 2 big components, 2 main components. One is called Ignition, it's a bytecode interpreter. And the second one is called Turbofan, it's the optimizing compiler. So bytecode interpreter actually means we transform JavaScript into bytecode and then interpret it. So it's not initially transformed into machine code, but bytecode, and we run an interpreter on that. And that whole process, transformation into bytecode and interpretation, is called Ignition. And then we have the second tier, Turbofan, which is an optimizing compiler. So that one actually generates native machine code. So why do we have these 2 big things? Why do we need 2 compilation tiers? We don't just add those because we like complexity so much, but there is a certain trade-off between those 2 things. Ignition, on the one hand, provides us with a fast startup. It has a low memory footprint, and so we get to execute the application, the JavaScript application, quickly. We don't use much memory, and we can observe it for a while. And also, Ignition handles all cases. So that means whatever crazy thing the application throws at us, we can handle it. Turbofan, on the other hand, requires a certain time of warm-up. So it requires the application to run for a while for us to observe it and to then optimize it. And that means we take longer to actually compile the application. And we only want to do that on a certain subset of your application. We don't want to optimize everything because that would just take up way too many resources. And Turbofan is the thing that provides peak performance. We take the pieces of your application that are really hot, really important, and spend time on optimizing those. So JavaScript initially is fed into Ignition. The unit of compilation for Ignition is a function, so we compile 1 function at a time. We parse the entire script, but we look at 1 function at a time, compile that to bytecode, and then start running it. We do that lazily. That means we don't do it for the entire script at once, but we do it for the function that is called first, and whenever that function calls another one, we look at that one. So it's basically the cost of compilation is distributed a little bit because we only need to look at 1 function at a time and don't stall the system for the entire script. What Ignition produces is, as I said, bytecode. This bytecode is then interpreted, and Ignition also does additional work that it would not need to do if Turbofan was not around. So you see this nice gift package at the bottom, feedback. Ignition collects feedback, so we observe the application and we look how it behaves, how certain pieces of the application behave. And just for Ignition's sake, we wouldn't need that, but we needed to later on optimize the code with Turbofan. So what Turbofan then consumes is this feedback, but also the bytecode. So Turbofan actually no longer looks at the source code, at the JavaScript source code. It just is based on this intermediate bytecode that we compiled. That has several advantages. One is if we decide to desugar certain language features on the bytecode level, Turbofan no longer has to worry about them. So we can basically reduce the complexity of the JavaScript application a little bit, make simpler bytecode out of it, and Turbofan only has to worry about this simple bytecode. And what Turbofan generates is actual machine code. It's actually natively running on the processor and hopefully gets almost close to native speed. So that's basically the holy grail of the compilation pipeline, to approach native speed. All right, let's take a look at one example. So this is a super trivial example, but stick with me, it gets tricky. The addition function that you see is basically just containing one arithmetic operation, one addition of two arguments that come in, and it's called from another function. So let's first look just at the first function, just at the addition function. What does an addition do? As we all know, it's overloaded, so it can do string addition, it could be an arithmetic addition, but it can also convert objects into primitive values. And what we see on the right-hand side is actually the specification. So that's what ECMAScript standard dictates that a JavaScript, a faithful ECMAScript implementation should do at an addition. And the actual addition is step 10. So all of the steps before are preparations to actually perform the arithmetic operation. And you can see that there are certain things that are specific to strings, but also these two primitive calls that are always kind of expected to be done by us. So, okay, if we want to compile add, we have to somehow implement that. So let's look at what toPrimitive actually does. toPrimitive, in the end, actually gets a method on the potential object that you pass in to be able to call a user-provided method to convert something to a primitive. Okay, so we get a method. How do we get a method? Get method actually means we need to do a property lookup potentially on the object, right? So, okay, what does property lookup mean? Well, okay, property lookup, we need to potentially go up the prototype chain, actually do multiple gets here. That's the yellow part that you can barely see there again. And okay, all of this is way too crazy already for it to be efficient and fast. So if we want to optimize, we actually don't want to do any of this. What we want to do is don't care about this. We only want to do the addition. And to some degree, that's actually what happens. What we do is we make some speculative assumptions about the input, about the left value x and the right value y. And that's where this combination of these two tiers helps us. So as I said, Ignition gathers feedback. So it kind of knew, okay, I only saw numbers at this addition site. And it tells the optimizing compiler, hey, you only have to worry about numbers because I saw numbers 500 times. So there will not be a string around. And Turbofan is like, yes, can do that. And Turbofan generates highly optimized code for exactly that kind of situation, because that was the situation that was observed before. But then on the 501st iteration, it might be that you suddenly pass in a string or an object. And that's where it gets a little bit hairy, because then Turbofan is out of luck. Turbofan is like, I don't know how to handle strings. So it needs to de-optimize back to Ignition. And you already see that there is a cycle forming here. So if we are not careful, we basically could run in cycles for a long time. And we need to prevent that, because every time we optimize, we need to spend a lot of time to perform smart optimizations in the compiler. And that takes memory. On a phone, that takes battery power. So we need to be really careful that every time we go around this circle, we actually learn something new. So the next time we go around this circle, Ignition needs to tell Turbofan, hey, you need to worry about numbers and strings, because I've seen both. And we had the optimization loops, that's what we call them a lot in the past, so that, that's the situation when you don't learn and when you just run around in circles and spend all of your time optimizing and de-optimizing. All right, so back to this example. So far we only have looked at the add function, but if we look a little bit broader, if we look at the entire script, or at least the two functions, we can actually see that we can be way smarter, because not only do we know that we pass numbers in, we pass actual constants in. And so that's where inlining comes into play. So if we were to inline the addition function into the f function, we could actually look at two functions at once. So initially I said we look at one function at a time, but Turbofan actually can perform inlining. So there we can look at two functions at a time or multiple functions at a time. All right, so far all we saved is one function call. So that's not that big of a deal. So why is inlining called the mother of all optimizations if it's just saving us function calls? The reason is that inlining enables us to have a broader scope, a broader view of the application, and thereby enables other further optimizations to apply. So inlining runs pretty early in the compilation phase, and then enables a lot of the powerful optimizations that come later to have more impact, to basically apply to a broader range. And in this case, one such optimization would be constant folding. So we could just see now, oh, in this one combined function that we have, we see two constants, they're being added. We don't need to worry about string or to primitive conversion, because we know they're primitive numbers. So we can just constant fold them. And that's basically, in a nutshell, what Turbofan does, kind of. Okay, I took a lot of slides to just explain that. One of my colleagues, Adi Osmani, actually can do that in one slide. So that's the recap. We take your JavaScript, we parse it, then one function at a time, we build abstract syntax tree and generate bytecode out of it. We run it for a while to gather feedback. Once we got feedback for these speculative optimizations, if it pays off, if we deem the function to be hot, we run it through Turbofan, optimize it, and compile it to actual machine code. So the thing that comes out is then specific to the underlying hardware that you're running on. And V8 currently supports 8 architectures. I'll leave it as an exercise for the listener to figure out which ones. All right, so that's the compilation pipeline so far. Which we overhauled the compilation pipeline over the last years. So Turbofan is a fairly new compiler. Ignition is a fairly new bytecode interpreter. What I mean by that is they're shipping for at most a year now, both of them. My personal definition for success that I always looked forward to in the years I worked on Turbofan was, once we can inline higher order array built-ins, I can declare success. And we can do this now, so yay. All right, let's look at higher order built-ins. Another example. Let's look at the reduce built-in of an array. Reduce with reduce you can, for example, express summation functions. So you have an array full of numbers, and you want to just calculate the sum of it. What you would write is potentially something like this. You provide a function to this higher order built-in, namely the arrow function that just takes an accumulator and some value and adds those two together. And you provide a starting value, like you start with 0 and just add on top of 0. For example, the array 1, 2, 3 would yield a sum of 6. All right, so how does Turbofan optimize this? Alles klar, ins Mikro sprechen. Bleibe ich jetzt da stehen. If you were to manually optimize this function, you would write something like this: a manual for loop with an index. You would iterate over it, And you would also have some accumulator called sum in this case. And yeah, so that's basically if you were to manually optimize it. Now the question is, can Turbofan actually reduce the left-hand side down to this? And the next few slides are to convince you that it actually can, I think. So let's look at the spec of reduce. Again, crazy stuff going on there, a lot of additional things that we didn't see in the hand-tuned version. And the reason for this is that the spec intentionally wants to be generic. So you can take the second order, the higher order built-ins of array and use it on other objects. You can come up with your own array implementation and just use the generic array functions. And the spec actually mentions this in a note. So there is this one note that says, oh, reduce function is intentionally generic. It does not require that this value is an actual array object. So all of the craziness that we saw that we see in the specification, where we have to worry about two-string conversion, the has property, the is callable check, all of that is intentionally there. And people are using these functions in a generic way. So we need to be faithful to the spec. If we are faithful to the spec, we end up with something like this. The function that we passed in is still being allocated at the beginning of foo. We have this addition function. Then we extract the length out of it. Then we actually have to check, is the function callable? Is it callable? Can we call it? Otherwise, we throw a type error. And then inside the loop, you actually see that we have to do a check whether the property is on the array itself or up the prototype chain. Again, that's dictated by the spec, so we have to do that. And we see that we have a function call in the loop. So especially the things in the loop are worrisome because they potentially get executed many, many times. So if we want to really optimize that, we should get the loop body as empty as possible. So the first step we see here is basically that we inlined the array reduce function itself. Turbofan did that. And on the right-hand side, we now see the steps that are applied afterwards by Turbofan to actually get rid of all the overhead that we see in there. So one such step is, for example, okay, the callability check is now kind of redundant because we see that thing we're calling is a function, so we don't need to check. This is basically that code. So Turbofan can remove it. Then we actually can inline the second call we had inside the loop. So we can, we no longer need to actually call a function. We can take the function body and inline it. So basically now we inlined twice already. So far this only got rid of the call, but in the next step we can, and this requires some explanation. So we can assume certain invariants of the array to hold. So an array internally for us can have multiple shapes. It can contain objects, it can contain double numbers, floating point numbers, it can contain integers, and another aspect, it could have holes or it can be packed. And packed means you don't have any holes, it's a contiguous array. It's really something that you normally call an array. And this is packed SMI basically means it's an array that is packed, that doesn't have holes, and that contains integral numbers, integer numbers, so no doubles. And that holds for the array we saw in the example before, right? Because it contained 1, 2, 3, nothing else. So no holes and integer numbers. And since Ignition observed this, Turbofan then relies on it. And that's the point where it relies on it. It puts in checks, and if this check fails, it de-optimizes. It actually says, okay, I now need to jump back to Ignition. Now, initially, this looks kind of useless because we don't gain anything from that itself, but it's again an enabler for optimizations that we apply then. So in the next step, for example, we can now see that since it is packed, there cannot be any holes. So this check whether the property actually is on the array or not is now redundant. And since this check is in the loop, this is super beneficial because that means on every iteration we can assume, the element is in the array. We don't need to walk up the prototype chain, and everything just becomes way simpler. And also on top of that, we can now see that since the array contains integral numbers, we can actually also do addition of numbers. So the addition again is specialized, as we saw in the previous, in the first example. And so by now the loop body actually already gets smaller and smaller. And with the last step, we can also remove the shape check, because in the loop body we see that the shape of the array cannot change. There is nothing that writes to the array, that deletes elements from the array, or that somehow changes its shape. Like, for example, if you were to freeze this array, this would be a major shape change, for example. And so now we can again remove a check inside the loop, and the loop body now is really optimal and actually resembles the handwritten version that we had before. And so this is almost the same as we had in the handwritten version before, and actually this the addition inside, if you would not inline the array reduce, the addition inside would, in the handwritten example, also be lowered to a number addition. So the loop body is exactly the same as we had in the handwritten example. All right. So I threw this at I wrote a simple micro benchmark just for this and measured the difference of the handwritten version and the one that is called Foo Manual, the dark blue one, and the light blue one is the one with the array reduce. And I compared an old version of V8 that didn't have the array the higher order built-in inlining, and there you see a major difference. So using the higher order array built-ins caused a major slowdown there. But with a recent version, so 6.6 was released I think a week ago or 2 weeks ago, you see that there is almost no difference. Differences of this tiny scale in micro benchmarks, they can just be order of instructions in the machine code, so that they are completely negligible. It could also be the other way around. So for all intents and purposes, the speed is same as the handwritten JavaScript version. So I hope I convinced you that Turbofan actually can turn the nicely idiomatic JavaScript second order array built-in into something that is as fast as the handwritten version. Yeah, it took us, Turbofan, it took us, I think, 4 years to get there. So Turbofan, we started writing from, we started to write Turbofan from scratch, basically. The only thing we reused from our old compiler was the assembler, so the thing that assembles machine code, that outputs the machine code. I mentioned we have 8 architectures, so we don't want to write 8 new assemblers. But other than that, everything in Turbofan is brand new and shiny. All right, let's do a recap. So I just showed one example with the array reduce, but the same principle applies to basically all the array built-ins you can think of, the higher order ones. So like map, filter, every, sum, reduce. There are also other built-ins that do similar things, that also have loops in them, for example, where basically you have exactly the same example, slightly different. That is for function apply or function.call. So all of those get optimized in the same way. And again, our optimizations are based on feedback that we got during ignition run. We inline known call targets, so that means if you add a certain use site of the second order built-in, always use the same function, we can inline it, so that has a major advantage if you don't put different functions into one place in array every, for example. Also, it assumes the shape is unchanged of the array. So basically, if in your function you start deleting elements from the array, that would defeat such optimizations. Or if you change, if you, for example, start putting double elements into this array within the function, all of that would mean that we couldn't remove these checks that are inside hot loop. So avoiding this shape change is good for performance. And also we specialize the arithmetic. So if most of the time you perform integer arithmetic, we learn from that and see, oh, we can produce better machine instructions. If then once in a while you throw a nan in there or a double number just to spice things up, then we need to de-optimize again and learn from that. That doesn't mean you cannot mix doubles and numbers. You can totally do that. It's just about the consistency of doing it. If you do it once in 1,000 occurrences, probably we optimized before. If you do it every other time, okay, we learn about it. So having consistent arithmetic inside the functions you pass to these built-ins also helps us to optimize better. All right, so that brings me to the final part of my talk, and that is JavaScript generators. So just by show of hands, who here has used JavaScript generators directly already? Okay, half of the room, I would say. Who here has used async functions, for example? A little bit more, okay. So JavaScript generators, they're the building blocks for async functions. So I will mostly talk about generators, and all of what I say basically applies to async functions as well, because they're based on generators. So before we talk about generators, we need to talk about JavaScript and the heap. And when I say the heap, I mean basically our garbage collected heap. So before I worked on Turbofan, I actually worked for years on the garbage collector. So I'm also, whenever I can throw some slides about objects and the object heap in there, I will do that. And so this slide basically shows that while we're running JavaScript, we populate this grab bag of things that we call the object heap. And inside there, you might have arbitrary objects that the application allocates, like an object literal, or if you say new array, all of this is a JavaScript visible object. We call this JS object, and I drew it yellow on this slide. It basically means, okay, the application can actually look at this object, touch it, it's visible to the application, it's useful to the application. Same for functions. They are also just objects floating around in this heap. And then on this heap, we also have internal objects that only the VM is allowed to touch and look at, but they're also part of this whole garbage collection scheme. So that has the advantage that we don't need to do explicit memory management for our internal metadata. We can rely on the garbage collector to handle both the application provided objects as well as the metadata. And the interesting part is even the code that we generate, the machine code, is inside this heap. So that means the garbage collector can also throw away machine code if it's no longer used. So if you have functions that get optimized and then all of a sudden you no longer use them, the code gets also collected eventually, if the function itself dies that holds on to it. Let's look at an example. And this example is basically trying to explain where variables can live. So sometimes they can, local variables can be on the machine stack, they can be local to a function, and sometimes they actually live on the heap. So they take part in this garbage collection scheme. In this example, we have a create function with a local variable x that is passed in as an argument. But the x is also used inside another function, right? Inside a closure. And what that means is that when create returns, the value of the variable is still held onto by f. So that means it actually needs to live somewhere that is longer than the lifetime of the create function. And what this means is basically the first time you call this create function with, for example, a value of 23 for x, we remember this value 23 in a canonical location in the heap. And this canonical location where we store these variables is called context. And the function binds this context. And if you look at the Wikipedia entry for closure, it actually kind of defines closures like this. It says a closure is a combination of a function and its execution environment. So the function itself, the behavior, is encoded in the code object, and the execution environment, the variables surrounding it, is encoded in the context. And also we put the feedback there. So we have another object where we gather all of this feedback about how the function behaves. If you call create again, you get a second closure, but the code actually can be shared. So that means when we optimize the function f later on, we only need to optimize it once, and we can share the underlying optimized implementation, even if the values are different for the context. And also the feedback is shared. So that means if you have multiple closures and you use the arithmetic in them consistently, optimization again benefits. So why am I talking so much about closures when we actually want to go to generators? Reason for that is that this scheme where we store variables on the heap is actually pretty useful when we talk about generators, because generators are functions that can be suspended mid-execution. If you yield inside a generator, it kind of returns, but remembers its execution state. And the execution state is kind of the same as this context that the closure binds. So let's finally look at an example with a generator. So in this case, we have a generator with 2 yield points and 1 return. So that basically means it can produce 3 values, and after that it will just say, I'm done. The first time we instantiate the generator, a JS function for it is created, and the generator object that is returned actually points to that function. So every time the generator is then invoked again and resumed again, we know which function to execute. And the context is also stored by the generator object. So that means we can resume the function with a certain execution environment. Now, all that's missing is basically to tell the function where it should resume, right? Because if we resume it from the top, it would have a different behavior. So we also store this continuation point. And the way we store it is actually we just number them. We number all of the yield points. We give them numbers from 0 to whatever. And that allows us, if you then call next on this generator for the first time, we basically call into this function. It knows, oh, my resume point was 0. It runs until the next yield point, returns a value, and updates this continuation. So the next time we call it, we know where to continue inside the generator. Also, all of the variables inside the generator are context allocated. So that means we don't need to worry about restoring them because they're already put on the heap. They're already put in a place where we can persist them. And that just continues on as long as you resume the generator. It always suspends itself at the next yield point. So that's for the object model. Now, how do we actually model the generator function itself? So again, I'll try to explain it with pseudo JavaScript. This time, this translation is not done by Turbofan, but by Ignition. So it's done the very first time you compile a generator. We do some translation to it to actually generate bytecode that more resembles as if you would have written this switch case on the right-hand side. The switch case contains some magic that you wouldn't be able to write in normal JavaScript, like accessing this continuation point, this special number. And it also, there are some scoping issues with it. So we basically need to create a scope around the entire function. But the bytecode, for all intents and purposes, has a switch inside. So every time we call this function, we read out the continuation point, dispatch to the correct point, and can continue running there. Now, the advantage of letting Ignition do that is, as I mentioned before, we can actually optimize this function. We don't need to teach Turbofan anything about generators because it just looks at a function that has a switch inside with this magic load of the continuation point. And that is super useful for us V8 engineers because we don't need to worry about generators in Turbofan at all, because Turbofan is complex enough without throwing generators in it. The very first implementation of generators used a different model, and basically we were never able to optimize the generator functions. Now with this we can. All right, so to recap, for generators, all the variables are stored on the heap. So that means they are no longer local to the stack of the function. Accesses to variables are a little bit slower. Generators are the main building blocks for async functions, so all of this applies to async functions as well. Internally, we translate to the switch, but other than that, all optimizations apply. So basically, the only drawback you get from generators is this slightly slower variable access. But the slower variable access you might have experienced with functions already, because as I showed in the previous examples, this context binding is not, context allocating of variables is nothing new. So in essence, the upside of that is we can optimize generators pretty good. So you shouldn't be afraid of using them. They should only get faster in the future. All right, and then we have the generator objects with the additional values. So there is a tiny overhead of additional memory that we need to hold on to, but also that is negligible, and you buy into the same machinery that was already there for context allocation of variables again. So there shouldn't be any major surprises in memory usage with generators. And with that, we're almost done. Already out of a voice. But I just wanted to remind you that you can actually follow us on Twitter now. So over the past, let's say, 1 year, 1.5 years, 2 years, we tried to improve our developer outreach. We tried to reach more people. We tried to not be this closed-off hidden V8 team that only looks at their micro benchmarks. We tried to look at real-world websites. I hope we improved over the past years. We have a Twitter channel now, and we have a developer, we have a DevRel person now. And so please follow us, tell us what are your problems. Let us know. We really want to optimize for the real web. We still have benchmarks that we optimize. We still care about benchmarks because that's our way of reasoning about performance. But we really want to hear your experience about, for example, generators or second-order built-ins. And by the way, it's this V8, ViennaJS. It's not that. Don't follow that. All right, with that, I'm finally done. Thanks for listening.